Okay. All right. So today we're going to look at a few examples. My plan was to get through at least 3 examples, but the previous section we had a good discussion, the second one, and it turned out that my solution may have been incorrect. So we don't know. We'll find out. So we got through only 2 examples. The other announcement I want to make is Friday quiz. The last Friday quiz will be this Friday, and the topic will be chapter 13. So combinational or sequential circuits. Okay. Okay. Next Monday, yes. Yeah, we will have something. I haven't decided yet what, but we'll have something. All right. So I went through the writing. Let's do this in chapter 1. Okay. So this is an ideal diode circuit. Okay, ideal diode circuit. All right. So a lively discussion. So the answer is already on there, but let's go over the steps. So we have a diode circuit. Let me change. That's an interesting color. All right. Okay, diode circuit with D1 at the top. 2 resistors, R1 and R2, both 1 kilo ohm, same value. We're applying V in, and V out is on the far right. Determine the transfer characteristics and plot them. That's the question being asked. Transfer characteristics, meaning the transfer function, is a ratio of V out to V in. How does the V out behave as a function of the applied input, right? So we are asked to plot V out or V in. We are not given any other information. Okay? We are not given any other information. The only information given to us is the circuit diagram and plot V out or V in. And of course, analyze using the ideal diode analysis model or ideal diode model. Okay, ideal diode model. So we don't know what V in is. V in could be DC, V in could be AC, square wave, sine wave. We don't know. Okay. But let's say V in is an AC that covers all values for V in, whether positive or whether negative. So if V in is a sine wave that looks like this, or maybe a square wave that looks like this, we can analyze for both half cycles, positive values as well as negative values. Right. Let's take a pause while you all write that down. Okay, shall we begin? A few more seconds. All right, so let's say V in is an AC input, right? So in the positive half cycle, what happens? We can redraw the circuit with V in like this, plus at the top, minus at the bottom. Okay. It doesn't matter if it's a sine wave or a square wave or a triangular wave, all values are positive. So we can model the input voltage as a DC battery. Be a sine wave goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 9, 8, 7, 6, 5, 4, 3, 2, 1. But all values are positive. If all values are positive, look at the diode. The anode is connected to the positive terminal, So for all values of V in greater than 0, diode will be forward bias. It's an ideal diode model, doesn't require anything except V in or the anode to be slightly larger than the cathode, or slightly higher in voltage than the cathode. If that's the case, it behaves like a short circuit, and we replace diode D1 with a short circuit. So if diode D1 is a short circuit, what is V out? Voltage across R2, because output's taken directly here across R2. And so what is the voltage across R2? So short, what happens to R1? There's no current flowing through R1. So it's not part of the circuit anymore. And so, even without looking at anything else, if you look at V out is connected directly to V in. So V out is equal to V in. If V in is 1 volt, V out is 1 volt. If V in is 2 volts, V out is 2 volts. If V in is 10 volts, V out is 10 volts. Right? V out is right here, directly across V in. This is because the diode behaves as a short circuit for any positive values of V in. It's forward bias. Okay, so fundamental principles, and we keep that in mind and simply apply those to your circuits. We already know ideal diode, forward bias, short circuit, reverse bias, open circuit. Then we have to determine whether it's open or whether it's short. Okay. All right, so now let's look at the negative half cycle. The negative half cycle, anode is lower than the cathode, diode D1 is off. And if diode D1 is off, it is replaced with an open circuit. And now R1 is in the circuit. And now we have as you stated earlier, what do we have? Jake? Absolutely. A voltage divider circuit. What is voltage division? Not just you, I'm asking everyone. Should ask your 201 instructors to change your grades back. Absolutely. I'll pat myself on the back because you were in my class. I'm just kidding around. It's fine. It's a long time ago. As a brief recap, voltage division and current division are shortcuts. They're based on Ohm's law. Simply allows us to skip one step, right? So voltage division applies to a series connection of resistors. And in this case, if we take a look at the perspective of, let me redraw it this way. If you look at this circuit, I can draw it like this. So in the negative half cycle, it's going to be minus plus, and my R1 and R2 are like this. My V out is here. This is R1. This is R2. Now, V out simply means, let's say you're taking a multimeter and connecting across R2 to measure. You're not actually connecting any component to R2. So R1 and R2 are in series because there is no other connection that is in the middle node. Okay. So if R1 and R2 are in series, current through those resistors remains the same. Voltage gets divided, and the division results in a fraction of the output voltage. So V out is simply the ratio of, is a fraction of V in, and the fraction is given by that resistor divided by the sum of all the resistors in that series connection. So R2 over R1 plus R2. And in this case, R1 and R2 are exactly the same. So V out, let me write it here, is V in times R2 or R1 plus R2. And because R1 and R2 are the same, it becomes half of V in. And then I had a minus sign in there. And so we don't need to have that because it's a negative half cycle, right? V in is -1, V out is -0.5. If V in is -2, negative half cycle, V out is -1, simply half because of R1 and R2. Does that make sense? Right? So if I was to plot the transfer characteristics, meaning V out as a function of V in the positive half cycle, V in is 1, 2, 3, 4, 5. Output is also 1, 2, 3, 4, 5. Slope of 1. Linear line at 45-degree angle. V out is equal to V in. And when V out goes, when V in goes negative, V out is half of V in. So -1, -2, -3, -5 results in -0.5, -1 to -2.5. The slope is -0.5. Let's take a pause. Let me know if you have any questions. All right, second problem. Shall we begin? Okay, as I said, similar circuit, except we now have an additional diode in there. This additional diode is a Zener diode. The value Zener voltage of 5 volts. Determine and plot the transfer function V out over V in. So let's again do the same thing. Forward bias, what happens? In the forward bias, if diodes D1 and D2 are forward bias, D1 is replaced with a short circuit. D2, what happens to D2 in forward bias? What happens to Zener diodes in forward bias? So voltage regulator, what's the voltage? So in forward bias, it would function as a regular diode. And so in forward bias, a Zener diode is also a short circuit. And so here, I would say both diodes are replaced with a short circuit. And because it's ideal diode, there would not be a voltage drop. It would simply be short circuits. And so circuit would reduce similar to what we had for the example 1 in the previous slide. And V out would simply be equal to V in. If V in is 1 volt, V out is 1 volt. If V in is 2 volts, V out is 2 volts, and so on and so forth. Okay. Make sense? Right? Circuit's the same. But now, when V in goes negative, if V in goes negative, that's when the Zener diode is reverse bias, and that's where we need to look at the value of VZ. So as long as V in is less than VZ, the diode remains off. Remember, Zener diodes work in the reverse bias, but as long as the input voltage, the Zener diode, is below the Zener voltage, the diode remains off, meaning it behaves like an open circuit. Okay. So as long as V in is less than VZ, in this case 5 volts, diode remains off. Okay. And if diode remains off, then D1, of course, is going to remain off or open circuit in the negative half cycle. D2 remains off as long as V in is less than 5 volts. And in this case, V out would still equal V in, because the circuit looks like this. This is open, so R2 is no longer in the picture, and V out is taken like this. Right? Connected directly to your voltage supply. It looks like a Thevenin equivalent circuit. There is a voltage source and there's a resistor R1. That resistor R1 is not connected to anything, so there is no current flowing through the circuit. If there is no current flowing through the circuit, there is no voltage drop across that resistor. If there is no voltage drop across the resistor, meaning voltage drop across the resistor is equal to 0 volts, that means the voltage at both ends of the resistor is exactly the same. Hence, V out is equal to V in. Make sense so far? Questions? Any questions? Again, negative half cycle, we would expect D1 to be off, D2 also to be off. Both are reverse bias. The Zener diode is reverse bias until the input voltage applied to the Zener exceeds the Zener voltage. If V in is greater than VZ, then it turns on in the reverse bias and it behaves like a constant voltage source of 5 volts. And this is where I confused myself. I'll explain. I'll go over the solutions that I had, and then I'll explain. Are we good up to so far? All right. So what happens when V in exceeds 5 volts? So when V in is greater than or equal to the Zener voltage, which in this case is 5 volts, then the diode turns on. When it turns on, it holds the voltage constant across it as 5 volts, right? So now V in is modeled this way. Diode D2 turns on. VZ is 5 volts. And now you have both R1 and R2 connected in the circuit. So my solution or my analysis was that V out would simply be half of V in, because you're taking the output across R1, between R1 and R2. So my analysis was that V out would be half of V in. Okay, half of V in. And so my transfer function, don't look at this for now. Okay, my transfer function V out or V in right here, in the positive cycle, VO is equal to V in, so we have a linear line. Right? In the negative cycle, as long as V in is less than 0.5, less than 5 volts, V out is equal to V in. So it's still a linear line all the way up to V in reaching 5 volts, minus 5 volts in the negative half cycle. And then the solution was V in greater than 5 volts, V out is half of V in. Okay. Does this make sense so far? Now, the student asks a question. If VZ is 5 volts, how can we take it as a short? Wouldn't we need to account for VZ? That's when I started doing the analysis, and I tied myself in knots. So the circuit would be something like this, right? This is the case for V in negative half cycle and greater than or equal to 5 volts. Okay. Negative cycle, V in is greater than or equal to 5 volts, or in this case, reverse bias, so minus 5 volts. And if it's greater, then my circuit looks like this. And V out is taken across R2 and VZ. Okay, VZ is constant 5 volts. And my V out is taken across the series combination of R2 and the Zener diode voltage of plus 5 volts. So V out should, or more likely than not, could be V in times R2 over R1 plus R2 plus constant 5 volts DC. And this is where we stopped. Well, stopped as in like we spent quite a bit of time to discuss this and see what I would have as my output. Okay. And so in the previous section, we had about 4 minutes left. That's where we ended the class, but we're still discussing this after class too. So I need to sit down at the start of class, more likely tomorrow, not today. And then I will go over the solution that I had, and I will look at the authors or the publisher's solutions and see whether this is correct or whether I'm making a mistake somewhere. Okay, yes. So the question being asked is, shouldn't the polarity of this Zener voltage be flipped? So that depends on if you're looking at just the diode or whether you're looking at just the Zener. So if it's just the diode voltage, meaning a Zener diode is always used in reverse bias. So if we take just diode voltage, then yes, this would be plus, this would be minus. But if we say Zener voltage, then this would still be plus, this would, I'm sorry, the other way around. Should be plus, should be minus. So it would be minus 5 volts. But since we're already saying it's in reverse bias, we don't apply a double negative to it. We simply say it's a Zener voltage of 5 volts. We don't say it's a Zener voltage of minus 5 volts, right? If, as an example, if you look at a spec sheet for a Zener diode, it'll simply say VZ of 5 volts or VZ 6 volts. It won't say VZ of minus 5 or minus 6 or minus 7. The negative or the reverse bias is implied. Because in the forward bias, it just works like a normal diode. In the reverse bias is where it actually matters. So Zener diodes are always used in reverse bias. So the negative is already implied. But yes, technically it would be minus 5 volts. Okay. And so for this section too, I will end class here today. And then we can discuss this, and I'll spend some more time just trying to see where I'm going wrong. Maybe I'm right. I don't know. Yeah, I thought I was right, but because of the student's question, as I said, I tied myself in knots, and so I just need to work through everything again, step by step. Okay. So if you wish, you can stay and we can discuss this. And if you wish to leave, you're feel free to leave. Okay. But as far as official class goes, we're going to end here today. Again, remember, quiz on Friday and then again next Monday. So Friday quiz will be the last one. That'll be the online system. And the Monday quiz will be the in-class quiz.